Wednesday, instead of double lecture, we'll have single lecture and then your first homework assignment. I will bring my bag of calculators so you can get used to using them. Although life tables don't require you to do much more than add, subtract, multiply, and divide, so it shouldn't be that hard. It's just a matter of keeping track of everything, which is why we use the life table to help us try to do that. And what I will do is I will bring the homework assignment with me, and then what I usually do is I'll release it on Canvas like 15 minutes before class, so that if you want to rework your homework or you lose your homework and you need to get it again, you'll have a copy of it there, and that's also where you're submitted. So it'll be submitted online, so that they all come into the same place and I don't have to worry about losing them in my office. I don't know if you've been in there, but it's a wreck. All right. So that's what we will do on Wednesday. I usually give you a week to turn in your homework assignment, but if you get on it and work at it, you probably will have it mostly, if not completely done by the end of class on Wednesday. Okay? I will have a key and I will be here. That's kind of the whole point of these second hours. So that you can ask me if you get off track and you can check your work as you're doing it. So that's kind of the idea. It's like study hall. All right, any questions or any other announcements? I did scan the key to the exam, but I haven't posted it. So I will post the key to the exam onto Canvas. I don't think I found any mistakes on it. I found mistakes on one of my exams, but I think this one's okay. So I'll post the key. It's in pink, for those of you who like pink. All right, we did the first part of this PowerPoint already. So we talked about demography. We talked about how the growth rate in a population is a balance between the birth rate, essentially, and the death rate. And then we often kind of ignore immigration, which can be good or bad, kind of depends on your situation. But we kind of assume it balances out in the end. We went ahead and defined mortality rate, which is your probability of dying at any given period of time. And then your probability of survival, which is the opposite, right? We talked about how it feels like mathematically they should be opposite numbers from each other, but they're not going to be exactly because of the way we calculate it. We'll get more to that. We talked about life expectancy versus lifespan, which made me change one of the questions on the exam. I had life expectancy, I think on the last one. Why do men have a longer life expectancy? And I changed it to lifespan to be more appropriate. It's been like that probably 15 years, but I changed it this year. And now we're ready for life tables. Okay. So we went ahead and did a little bit of this. We said that life tables are systematic. That's the table part. So we're going to organize our data in a way that we hopefully can understand it. And they're built by looking at cohorts. And we define cohorts as being individuals born at the same time period. And I told you we use that kind of loosely. Okay. So we are going to group them according to age groups. But we won't necessarily always follow a cohort, which will become more obvious on the next slide. And then just generally in English, we use cohort just to describe any group that's starting something at the same time. So like all the freshmen that started UTM this year, they're a cohort and stuff like that. All right. Now let's get into it. There are two types of life tables. The first one is called a cohort life table, sometimes also called a dynamic life table. And I mentioned this one last time to kind of get you to think about how we would collect data to create life tables. And so in a cohort or dynamic life table, what you do is you go out and you find the individuals born, let's say this summer. We're going to put radio tags on them, and then we're going to follow them their entire life and collect the data on that group. That's a cohort life table. On that single group, we follow a single cohort. This requires a lot of effort, money, and time to do. It is done. And so there's a which school is it? I can't remember if it's ETSU or Tech, but they have a Duck Guy, and they have been putting tags.
It's Tennessee Tech.
Tennessee Tech. It's Tech. They've been putting duck tags on mallards and following them for years now, right? For several years. They could collect this kind of information, right? But they're probably not doing a cohort life table. They're probably doing that little bullet underneath. They're probably doing a dynamic composite life table, meaning that we're going to mark everybody that we can get a hold of this year. So all the ducks that hatch this year, we're going to get them, mark them. And then next year, we're going to get all the ducks that we can get and mark them. And then next year, we're going to get them, and we're just going to follow all of them. Okay, so we're still following cohorts, but we're following multiple ones at the same time. So if you've got the money to do it, which he seems to, and the time. I don't have the time to do it. We're at different institutions, right? He's got graduate students. We don't do that here. Then you might do it. This is not the most common type of life table, though. Most people don't have the time and money. The game and fish, which you're setting, which I told you last time, use life tables to set their bag limits and things. They're not doing this for the most part. They're going to use the second type of life table. Before we move this, though, before I put the second one up, before I put the next one up, stupid clouds. We're going to see this words dynamic and static quite a bit. So I'll go ahead and put the word up there. Dynamic means that it's changing, and static tends to mean that we're looking at like a single point in time for the most part. And so kind of keep that in mind. In this case, dynamic, in terms of dynamic life table, means that you're following these across their lifetime. And static in this case is we're taking a snapshot, which is pretty common for static. So we're going to go out and sample the population. We're going to have a technique for aging the individuals in that population. And then we'll build our life table based on that sample. So that's going to be called a time-specific life table. A time-specific life table, or a static life table. And so this is what you would do at a check station. I did them a lot when I was an undergrad. They were pretty fun. I enjoyed doing it. They would bring the deer in, we'd pop the jaws out, and we'd age them based on the wear and tear of their teeth. And we report that information, and we go into a database, which was a fancy word for life table. And that would tell them about the population and what they should be setting as their bag limits in different areas. Probably the most fun I had those, we also did a raccoon check station. Did you ever get a chance to do that? That was pretty fun. We learned how to age the raccoons. And every once in a while the dogs would run through where we were set up, where the check station was set up, so it was fun. We were out late, of course, but it was really fun. And I don't think I could tell you how to age a raccoon now. What now?
Was it just for like open hunts, or was it like to check for rabies and stuff?
We didn't check for rabies, we aged. We were doing it. But I think it was part of the, I think we were doing a specific area, and it was part, when I was an undergrad here, the guy who taught mammalogy was a PhD student at Memphis. He didn't have his PhD yet. We would call that ABD. So he was teaching just the mammalogy class and commuting from Memphis. And I think that was part of his research, and he was using us as labor, basically, which is pretty common. But it was fun. It was a great opportunity. Mm-hmm. Okay, so that's the idea. So this is a little bit easier to do as long as you have a good technique for aging animals. Okay, so we saw that with the eastern bluebirds, but we also saw that we didn't have fine detail. We could only tell them basically if they were a year old or more than a year old, right? You could do it with mourning doves. You'll probably have done that in one of your management classes for you interim folks. You can do it, of course, with deer, raccoons, you can do it, and so forth. All right, any questions between cohort life table and a time-specific life table? We will be calculating time-specific life tables. So we're going to go out, collect data, and put it into we're not really going to go out. We don't have animal ecology lab anymore, but you can do it in your applied ecology lab, right? All right, so to put the life table together, we need to understand how what's on this slide works. I don't know the proper name for it really. It's something that you probably should have gotten when you were in algebra or maybe even in chemistry a little bit. But I'm really going to harp on this stuff quite a lot because I find that some students have it and you're already bored. You're like, I got this, and some students don't. So we're going to take a few minutes. We're going to have X, and X is going to be our age. And a lot of time our ages are going to be a span. So like if we go on to the next slide, did it come up? Yeah. So we're going to work with gray squirrels as our first example. And so X is it's actually organisms that are 0 to 1 years old. okay, or 1 to 2 years old, or 3 to 3 years old. That's pretty common in these aging techniques. A lot of times they're going to give you within a season, or within a life stage, or within a range of ages, right? That's typically what they do. They usually aren't going to be able to tell you the day they were born, right? And so you'll group them according to a time period that is reasonable for the group that you're working with. And I'm saying it that way because for squirrels, years is appropriate, and that's what this is representing. And so a squirrel that's 0 to 1 years old would be in that first category. On your homework, I'm going to give you an example with frogs. And with frogs, it's going to have eggs, tadpoles, froglets, which is right as they're metamorphosing in frogs, right? That's not going to be years by any means between those stages, but it is an appropriate way to look at what's happening to the life expectancy in that particular group. Does that make sense so far? Okay. As we're looking at these, as far as what we will use as x will be the first number of the range. And so this one is going to be x at time 0, x at time 1, x at time 2, and so forth. We will use the first number of the range for everything that we do. Okay. This takes us back over here for a second. So for example, if I say in x, which would be the number of individuals at that particular age category, whatever it happens to be, then that means that the n, the number, of course, you'd put the actual number in, but the n is going to change for each time period. And so we would have n0 for those that are 0 to 1 years old, n1 for those that are 1 to 2 years old, and so forth. And for the first time, I noticed that I have lowercase n's and uppercase n's there. Most of the formulas have lowercase. Doesn't really matter though. Either way, it's just number. That's what the n is for, is number. So the number that you have at year 0, the number that you have at year 1, the number that you have at year 2, and so forth. We're going to take these representations, I guess. I don't have a proper word again. Gosh, the cloud really need the clouds to lift. As we go forward into doing population models as well. And in the population models, we'll start with N0 all the time. So N0 meaning the population size at time 0. That's generally what that means. Okay, so N0 we'll see quite a lot. All right, any questions about any of that so far? So like I said, I'm going to harp on it a little bit. So we go back to our gray squirrel table, life table. And so N0 in this particular life table is 530. That's how many squirrels were around. We will view it as how many squirrels were born, although technically between 0 and 1 you could lose a few. But we're not going to know that till the next time period. Think if this is remember that this is a time-specific or static life table. And so what we did is we went out, we captured a bunch of squirrels and aged them. And so we don't know where within that year the 530 squirrels are. Are they a month old or 3 months old? Essentially is what I'm getting at. But we know that all 530 were born in that year. Everybody understand so far? That's kind of important moving forward as we interpret. That's a lot of this one is interpreting what these things mean. All right, and then the next year we had 159, so that's N1. And so what would the 5 right here be? That would be N5, right? It's the first number. So this will be N3, N4, N5, N6 right here. 21, 5, and 0. All right. What's this tell you about squirrels? How long do they live?
Not really.
I feel like that's probably not bad for a squirrel. Get up to 6 years, 5 to 6 years anyway. Probably not too bad. There are a lot of hawks on campus. How long do you think our campus squirrels live?
Especially compared to like possums. Possums make me sad when they live in like what, 3,
I don't know.
4, 5 years.
No idea. I mean, if you had a pet squirrel, it could probably live longer as long as you had a way to keep a hawk from getting it. It's kind of like your pet cat. Your pet cat can live a long time unless you leave it out in the yard with a great horned owl. That's just life. Okay, No, I don't think that's too bad for squirrels. But they probably, you know, they're a little bit disposable. All right, let's go ahead and look at the first couple of parts of the life table, save us some time on Wednesday. And so as we're going into this one, you've got a lowercase l. We do have to be very specific on this one because later in the life table, we're going to have an uppercase L, and they mean very different things, and we use them in different ways. So this is a lowercase l, and then X, representing our time period again. And as we go through this, I am going to give you formulas on how to calculate these columns. However, that should become a skill or a, a muscle memory type of situation. Right? So I'm not going to give you formulas on the exam. And one way to do that would be to memorize these formulas, but another way would be to understand what these columns are representing. That's what I'm getting at. Okay? And so as we look at this, let's look at the definition first. So LX, lowercase lx, is the proportion of individuals surviving at the beginning of each age class. At the beginning of each age class. And so without doing any calculations, for L0, all the squirrels in this case are alive at the start of that time period. And so that's going to be 1, representing 100% are alive. Without even using the formula. Okay. This is called the survivorship. That's in red and underlined. I should at least say it right. And one of the things that's important here is we will end up graphing this column. That's part of the reason it's in red and underlined. So we will make survivorship curves. And we're going to talk about the 3 main types of survivorship curves. I'm going to talk to you about how to interpret them looking at the data with your graph. Try to. And then when you do your homework, you'll do your life table. You'll draw a survivorship curve and a mortality curve, which we're not to yet. And then I'll ask you what type of survivorship it represents. Okay, so this is an important column that you make sure you understand what's going on. All right, let's look at the actual formula. You've got Lx, which tells us that that's going to be different for each of our time periods. We're going to have an L0, L1, L2, L3, L4, L5, L6. And then we have it equals Nx, which tells us that number is going to change for each time period. N0, N1, N2, N3, and so forth. Divided by N0, which means we're always comparing back to the original number. That number does not change. It's always N0. And so if we start with L0, then what we do is we put 0 everywhere that we have x's. So L0 equals N0, in this case divided by N0. Your x's have to match. Your x's have to match. And that's going to hopefully keep you on the appropriate lines as you're going through, which is one of the common errors I see really later in the life table, not so much this early. It's making sure you're pulling everything from the right line. And so for the first one, like I said, if we're doing L0, we're always going to use the first number, so we're doing L0. It's going to be N0, which is 530, divided by N0, which is 530, and that's going to equal 1. Another thing I'm going to ask you to do on your homework is to interpret these values. And so for this one, that 1 means 100% of the original cohort, because we're always comparing back to N0, so it's always going to be compared to the original cohort, are alive at the beginning of year 0. So everybody was born. A little misleading, right? Could have had a few miscarriages and things. But we're just going to assume that everybody was born, and that's where we started out. All right, as we move down to L1, now we want to do L1 here, And this will become N1 up here. And so L1 then becomes 159 divided by 530, and that should give us 0.3. Which would be 30% of the original cohort are alive at the beginning of year 1. And then I went ahead and put L2 here to keep us going. And so again, if this is L2, this becomes N2. And so N2 is 80 divided by the original cohort number, which is 530. And then 15% of the original cohort are alive at the beginning of year 2. And you'll notice here I actually did 6 for you. So I've got the bookends, right? So L0, everybody's alive, everybody was born. This is the cohort that we're starting out with. 100% of the squirrels are alive. At year 6, we've accounted for everybody. Everybody has died at this point. And so 0% of our original cohort survives to year 6. Okay, this one's fairly easy to interpret in that way. The main key here is we're comparing back to the original number. Any questions about LX, lowercase lx? All right. So here's dx, lowercase d, although there's not another d in there, but still lowercase d. This is the fraction of the cohort that died. And so it is a measure of mortality, but it's not the one that we're going to be interested in. We're going to need it later, but we don't need it right. We don't need to graph it, is what I'm trying to get at. So we're going to graph survivorship, which was the LX, and we're going to graph mortality, but it's actually going to be the QX, which we're not to yet. And part of the reason for that is this is your mortality compared to your original number. And the next one is going to be how many are dying in each specific cohort, which is what we're more interested in. So what are your odds of surviving that particular year is the next one. This one is comparing back to the original number. I know that it's comparing back to the original number because if I look at the formula, I've got n sub 0 again, which means it's not changing. So again, every time you change from one age group to the next, you have to change out all the x's. And so for D0, going back to our original cohort, then this is going to become N0 minus N0 plus 1. All right. One of the things that I'm too short to point to, maybe this will give me just enough. Yeah, that'll give me just enough reach. Is that this x minus 1 is a subscript. Okay? And therefore, what it's referring to is x in this case, which would be 0, because we're doing D0. So that's going to be 0 plus 1, which is 1. And so this becomes N1. Okay. For some reason, probably mostly when you start writing it by hand, sometimes this will become Nx plus 1, and that of course is going to get you a completely different number. Okay. And so this is all a subscript, and it's referring to what n you're going to be using. Okay, does everybody understand? Try to avoid that common mistake. Okay, and so that means we're going to be at 530 minus the next year, which is 159, and this time we're always dividing back by the original, so 530. That gives us 0.7, or 70% of the original cohort died between years 0 and 1. That's the other thing that's kind of weird when you're interpreting this particular column, is it's telling you what percent of the original number died in each of the time periods. And so if we go to, well, first of all, this is where you really start getting into your rhythms a little bit. And so the first one is going to be this minus this divided by this. And the next one is this one minus this one divided by this. And then this minus this divided by this. Right? It's a rhythm that you're actually doing. You don't need the formula for that necessarily once you get a hang of it. It's probably easier with what I just said. This minus this divided by this. This minus this divided by this. Although I would say that when you start doing that, just make sure you're staying on the right line when you write your answer. Don't get off a line. Okay, does everybody understand what I'm saying? Did you understand my this and this and this? Okay. Let's look at one of these numbers to do another interpretation. So if we look at year 4, right, we're going by that first number. So we want to do D4. So if I ask you to interpret the value for D4, you'll come over here and you'll see it's 0.03. And so that is 3% of the original cohort. 3% of the original cohort died between years 4 and 5. So I got that? 1% for the next one. 1% of the original cohort died between years 5 and 6. So you need to be very specific in your interpretations. I feel like there was something else in my brain I was going to tell you. All right, anything that y'all see that you need to know about this one?
Was it the note that the total of that column should be 1?
Probably so.
It's
Yeah.
in there.
It is on the slide, just not in my
That
brain.
one looks important.
It is.
Because everyone's dead. Yeah.
Yep, you have to account for everybody in the cohort. And so that one should add up to 1.0. And this is just a way to make sure that you're on track. That's all. It's not anything that means anything other than that. And so if you add that up and it doesn't add to 1.0, you're off somewhere. Good catch. Okay. Anything else I missed on this slide? Let's do one more column, and then we might call it a day before we do the last two, especially because we got a couple of people out today. So the next column is QX. QX. And this one is your age-specific mortality rate. And this is the one we will graph. That's why I have the mortality there in red and underlined. So this is the second graph that we're going to make for each of our life tables. And what makes this age-specific is because this time, this formula is exactly the same as our previous one, except for one thing. And that is we're going to let the lower number change now. Okay? That's the only difference between this formula and the last formula. So instead of comparing back to the original cohort every time, we're going to just be doing that same year. We're going to compare back the year. We're going to compare 1 year at a time, basically. And so if we start with Q sub 0, all of those x's become zeros in our formula. And so that's going to be 530 minus the next year, so minus 159, divided by 530 because it's in sub 0. And this would be another check on your life table, right? These two numbers should be the same in your life table every time. Okay? The rest of them are going to be different, but these two should always be the same. So it really doesn't get interesting until we do Q1. And we change all the x's in our formulas to 1, which means that we want N1 minus N2 divided by N1. then the next one's going to be, so that one is going to be 159 minus 80 divided by 159, and then 80 minus 48 divided by 80, 48 minus 21 divided by 48, and so forth. I find it slows me down looking at the formula, but I've done them a lot. As far as interpreting it, the biggest difference here is we're looking at the age-specific mortality. So we're looking at the mortality in that specific group. So for Q0, up here at the top, we already know that that was the percent of individuals, the original cohort that died, but it's also in 0. And so it's the number of individuals that died between year 0 and 1, right? So died by the end of the first year. Let's do one in between, because it looks like I did the 2 ends again. So let's do year 3. And so for year 3, we got a QX of 0.55. And so that would be 55% of the individuals that were alive at the beginning of year 3 died before the end of that year. They died between year 3 and 4. They died in that specific time period. That's what I'm looking for, is that you can make it clear to me they died in this time period. So far, so good? All right. The reason why I pulled the Q5 down here is because we get a 1, and you should always have a 1. Another check here if you want. You should always have a 1 right here, and then a 0. And what this represents is that 100% of the individuals that were alive at the beginning of year 6 died before the end of the year. Also meaning we have now accounted for all our squirrels. So survivorship's a more fun topic, but you know, mortality is good too, right?
I like the math on mortality better.
All right, I'm going to go ahead and point this out, and then I'll reinforce it like that on Wednesday. No, I won't. But I will hopefully reinforce it and again on Wednesday, and say it probably a bunch of times on Wednesday. We are going to make 2 graphs. We're going to graph this column and this column. And at some point I've got one of these life tables, I think, that's got asterisks over it to also remind you. And so this is going to be our survivorship curve, and this one's going to be our mortality curve. When we graph our survivorship, this 0 is important, because what that means is nobody is surviving past that point. And so we will graph this 0. That usually is not a problem. Occasionally I'll get somebody who leaves the 0 off, but mostly we seem good with that. The main problem I get is on this curve. It stops here with 100% of everybody dead. Because if you go down to the next one, everybody comes back to life. And you have 0% mortality, and that's exactly what the graph says, that all of a sudden all the squirrels come back to life. All right? I realize, is today October 1st or tomorrow? Tomorrow. Tomorrow's October 1st. But we don't want zombie squirrels or zombie frogs or zombies, whatever your problem is, running around. And so a lot of the mistakes that I see when we're working with life tables and interpreting this stuff is that you just need to take like 3 more minutes and think about it. Okay? Just think about what that graph is saying, just for 1 extra second. And then you'll understand why we stop this curve at 100% dead, and we don't go from 100% dead to every squirrel alive. Okay? The other thing I will tell you is sometimes on the homework, on the homework I'm giving you next time, I've got a word problem, essentially. Basically, it's not that hard in this particular case. It just says we had this many eggs, this many tadpoles, this many frogs, that kind of thing. And you build your own life table. So you draw your own life table. And then I get questions about this last line right here. All right. You don't necessarily need that last line. However, it is a good check to make sure you're zeroing out. So I always put it in. I think what the problem on that homework assignment is that we have, like, I think it's eggs, tadpoles, froglets, frogs, and you don't have anything to call that bottom line, which is fine. But that doesn't mean, I think that's the main time I end up losing this 0 if you don't have that bottom line when you're making this graph. And you do need that 0. Does that all make sense? Okay. And so if you get a life table that doesn't have the 0 row, I usually just go ahead and write my zeros in and make sure I'm on track. Because if you end up with a number down here, something's wrong. You're off somewhere. All right. Any questions on how to interpret the first 5 columns? All right, the last 3 columns is how we get the life expectancy. As defined as we already have, how many years they have left to live. But the 2 columns that we do to get there, we won't interpret like we've been doing here. We'll learn what they are, and what they are is going to be kind of gibberishy, but they're like time units and things like that. And then when we get to the life expectancy, that's the column that we, of course, want to be able to interpret again. But those 3 columns, I want to be able to do at the same time, and I want to be able to do them correctly. For one of them, there is no formula. It's a method only. There's no nice formula for it, and so we'll need to do that. All right, and so I think we'll do that on Wednesday. Bring your first homework assignment.